Hello everyone, I'm Zhenyu Hou, and today I will present my paper and from Gaussian process to ellipsoidal obstacles, safety control barrier function, and multi-predictive control. Now let's start our motivation. Autonomous ground robots navigation in complex and unobstructed terrains becomes more and more important. And there are two challenges arise: how to represent terrain and how to navigate safely. And this makes traversability assessment and safety control becomes more and more important. And identifying risk and minimizing collisions becomes more and more important. Now let's talk about the related works. Recent approaches to safety navigation on the uneven terrain can be broadly categorized into two directions: GP-based methods and control barrier functions-based methods. And the GP-based methods, it can smooth representations of terrain, but it is heavier and it didn't recognize and response in the in the highly dynamic obstacles. Mm, and control barrier function based methods, it can ensure the safety, but it didn't model dependent and it didn't describe the obstacles continuous. These two limitations product our methods. We can solve these two problems, not only safety but also the continuous about the obstacles. We built a GP process over the terrains to produce a high-resolution traversability map and uncertainty fields. And from GP gradients, we built stochastic control barrier functions with ellipsos safety certificates inflated by the posterior covariance. And these certificates are embedded as core constraints in the convex modern predictive control and embedding the real-time safety control with providing forward invariance. And this picture is our simulation navigation experiments in the Unity, and this is our real-world experiments. This is our hardware, and this is autonomous navigation in the uneven terrain in our methods. This is our works. This is our overview, our framework overview, and you can see our framework integrates the layer-based localization and the GP terrain pose mapping and the control barrier functions safety certification and the modern predictive control. It unified the pipeline and embedding the robots can generate uncertainty-aware traversability maps and to guarantee safety and fast navigation for our robots in the uneven terrain. This is our methodology. We used a spiral Gaussian process with an RBF kernel, and the input is the local point clouds and height gradients, and output is the traversability mean and variance. And the gradient fields reflected the slope and the local changes, and while the variance quantified how uncertainty were at each localization. Uh, Now let's bring to the uncertainty into the safety, and we encode the safety with an control barrier function. And when traversability is low or uncertainty is high, and then and then we can build it as an uncertainty margin autonomously. The safety buffers where the observations as the spatial and the terrain changes rapidly. And but maybe you will ask, how do we get the computable geometry? We can approximately risk sets with a minimum volume enclosing like this. We can build the obstacles and the region shift vertification as a ape loops, and the ape loops, the minimized ape loops can representation our obstacles, and we can inflate each its ape loops into the local GP variancy, and finally we can do the Taylor expansion like this. And this picture shows our GP, CPF, and MPC methods in the autonomous navigation, with dynamic obstacles. This is a GP control barrier function we can build with the Gaussian process. And this is the RBF kernel, and this is the gradient fields, and this is a standard variancy. And we can guarantee the safety under the control. Now let's go to the MPC formulation and the closed loop safety. And to generate dynamic, feasible, and collision-free trajectory, we embed the ape loops barrier functions into MPC methods, and at each map, each time step, controller source can writing like this, and the discrete dynamic and the barrier delay constraint like this. Finally, we can close the loops hours in the MPCC algorithm. Each state screens can obey like these methods. And in the right picture, it is our all algorithm. You can see how our algorithm guarantee the visa control barrier function. Now let's talk about the experiments and the results. We do our experiments in the gazebo simulation, and we validate our GPCBF MPC function framework through extensive tests on the understructive, uneven terrain, and a lot of other types of terrains. And we control our methods with two baselines: the spiral Gaussian process-based terrain assessment pipeline and the classical dynamic control barrier function MPC methods, and across diverse terrains and control performance and navigation reliability. You can see this picture. You can see this picture, and our methods is B and E. You can see we demonstrate our methods in this uneven terrain with the dynamic obstacles avoidance, and the green circle shows our methods can collision free in this occasion, and the yellow one, it is as a safety area, but the classical spatial Gaussian approach, like the C and F, is filled with the dynamic obstacles. You can see it crash at this place. The A and D shows the original uneven terrain, and the later based the local map. And this slide shows the shows the four types terrains in our experiment. So in gazebo, and this is a grass, and this is This is a grassland. This is the urban ruins, and this is the sand dunes, and this is the desert. We can show our algorithm in these four high resolution simulators as environments. And the under pictures displays the later point clouds collected by the differential drive robots under those conditions. And this experiment shows our shows our modeling ability in the uneven terrain. The left picture shows the envelopes generated by the dynamic control barrier function, modern predictive control methods for a differential car navigating in the uneven terrain. The yellow circles markers the missing terrain obstacles. And the middle one, it shows our simulations and navigating in the ICAC scene. And we also use the differential ball car. And the right guy, it shows the same conditions, the same map, same localization, use the same robots, and later our approach, GP, and MPC algorithm, it can successfully capture the majority of obstacles envelopes, and the yellow arrows highlight the regions correct modeling by our methods, but it didn't modeling by the DCBF MPC methods. This is all our experiments. And in summary, we proposed envelopes safety certificates by the Gaussian process, uncertainty solves, and a high resolution map and a high computing MPC methods, and it can solve at real time and provide the safety navigation on the challenging terrain. In the future, and I hope our methods can implicated in the Akuman cars or Omni dynamic models, and I try to I try to implicate my methods into more and more real world experiments, and try to in the future consider the SE sense dynamic models and or connected with the learning based methods. And in this work, I didn't focus on the trajectory optimization. Maybe its trajectory it isn't smooth. So in the future, I hope we can change this changes by the optimization methods. That's all. And thank you for watching. And I'm happy to answer all your questions.